thanks Antoine and Freddy for giving me this opportunity to present my work. So I will be talking about the role of breaking waves in ocean-atmosphere interactions. I did this work I did most of the work that I will be presenting while I was postdoc with Ken Melville at the Scripps Institution of Oceanography in San Diego. And this work has been also done largely in collaboration with Stéphane Popiner, who is in Paris. So I want to start with this picture, which shows a lot of what I'm going to be talking about today. So it's a picture I took from research platform Flip in the Pacific Ocean just after a big breaking wave. So you can see here the boom where we were putting the instruments. And what you see is basically a very rough surface, and then you see air bubbles that have been entrained, and that give this white color. I mean, at the surface of the ocean, and bubbles are present at the surface and below. And I will be talking a lot about and trying to understand this two-phase. So two-phase in the sense air and water turbulent flow that's arising just after breaking events. The reason to study wave breaking in ocean-atmosphere interaction is because it moderates or controls a lot of these interactions. So this is a video also taken from Flip, but that was done by Fabrice Véron a few years back, and it's fairly high wind speed, so it's around 16 meters per second, and the significant wave height. So the height peak to crest, the typical height peak to crest is almost 5 meters, so it's a pretty rough sea. And you can see that you have a lot of these white patches, or called white caps, that are the visible signature of breaking event. And so wave breaking is going to dissipate energy. It's the main process that dissipates energy at the ocean surface. So it's the reason why you have some limiting height for the wave. So even if the wind blows incredibly fast, at some point wave become unstable and break, and so you have some limiting height. And then by breaking, it's going to transfer momentum from the wave field to the upper ocean. So momentum is transferred from the wind to the wave, and then from the wave to the upper ocean, and generate currents, and so participate in the development of larger structure. And then it's transferring mass. It's transferring mass in both directions, in the sense that you're going to bring stuff from the atmosphere to the ocean, and you're going to bring things from the ocean to the atmosphere. That's what I will be focusing today. It's going to be on mass transfer and its impact on climate. So the first type of transfer is sea spray. So the generation of water droplets that goes to the air. So you have two main pathways to generate drops. The first one is the direct wave atomization, either when the wave breaks and it impacts and it creates drops, or when the wing is tearing apart the crest of the wave. So that typically generates big droplets. And then the second pathway is directly related to the bubbles that are unchained by breaking waves. So bubbles are unchained, and then they rise at the surface, and once they are at the surface, they get stuck at the surface. You have a thin film that separates the bubble from the atmosphere. The film drains, and then the bubble bursts. And when it bursts, it ejects small droplets that are called film drops, and then the cavity retracts and shoots a jet, which generate jet drops. So all of this creates some drops that are, and then the small one then can be transported up into the atmosphere, where they may evaporate and leave sea salt particles or biological particles, which are going to enter which are going to enter processes around cloud. So they can serve as cloud condensation nuclei. So these are all the reasons why we should look at sea spray and how breaking and waves affect generation of sea spray. But today's topic is really going to be about the bubbles. So breaking wave entrain like a large pocket of air, and that's why we see these white patches when you're at fairly high wind speed. And then these bubbles, they stay sometime. They stay sometime in the water. The small one can be transported down by other processes, and through their lifetime in the water, they are gonna transfer gas, and it's a process that's only bringing gas from the atmosphere to the ocean. And this is a big deal for several gases, and in particular, if you want to quantify in more detail how much carbon that's in the atmosphere goes into the ocean. So how is the gas transfer physically modeled? So the kind of the classic way, or the way people have started parameterizing or modeling gas transfer is fairly simple. So you have concentration of some gas in the air, concentration of some gas in the water, the concentration at the surface. So concentration in the air is related to the one at the surface through the solubility of the gas. And then you write a flux F between the two phases. And this flux is written as a transfer velocity times the concentration difference. And so all you need to do is then to understand, you're basically hiding or putting all the physics of the transfer into the transfer velocity, and how you're going to parameterize or model your transfer velocity. And what's typically used is to say that the transfer velocity is going to depend mainly on two variables. One is the Schmidt number. So the Schmidt number is the ratio of the viscosity, so the diffusion of momentum, to the diffusivity d, which is the diffusion of mass. Yes.
When you say surface is a kind of idealized thin layer.
Yes. Yeah. I mean, it could be any surface, basically. It could be just a flat surface, then you're going to have some exponent for the Schmidt number. It could be a rough surface, then it's going to change the details of the exchange at the interface, and then this exponent might be changed. So you actually have, I'm not going to talk about, but you have and then if you have turbulence in both phases, even if the surface is unbroken, that's going to change your transfer rate. Does that answer your question, or? Okay.
What is the upper bound for U10 for this formula to be valid?
That's like the whole talk, so I'm gonna go to it. So okay, and then the second term in this in these parameters. Okay, yeah.
Is the viscosity of the water or the air?
The one from the water.
Okay. And
diffusivity in the water.
Okay,
yeah.
thanks.
And so then you kind of hide all the dynamic into the wind speed dependency, and then the intuitive idea is to say, okay, if you have more wind, you're going to have more wave, you're going to have more braking, more turbulence. So obviously the transfer velocity should increase with the wind speed to some power. And the question is the wind speed good enough to describe these processes?
So why should it be a power law with respect to
just
the
because that's
velocity,
the simplest stuff to fit to data. There is no reason behind. It's just that, I mean, it basically comes from these kind of graph where so I describe this slide, and then you tell me if it answers your question. So on this plot, it's a busy plot. I'm going to spend some time on it. So this comes from a review from Garb in 2014. So he has collected a bunch of data on a bunch of field measurements of the transfer velocity of two gases. So you have two gases. One is DMS, which is related to biological activity, and one is CO2. So DMS are the red circle, and the squares correspond to CO2. And so first thing is, okay, and then the plot takes into account the effect of the Schmidt number. So it's this transfer velocity is normalized in a way that should take into account the difference in diffusivity between the two gases, so that you can only look at the dependency in wind speed. So you have two parts in the plot. The first one is when you are at a fairly low wind speed, so below 6 or 7 or 8 meters per second. You have very few braking events. And so it increases smoothly, it increases linearly, all the points are more or less superposed to each other, and so this kind of parameterization are going to work very well. When you go above a certain threshold, around 8 meters per second, you start having a lot of braking events, and it gets more complicated. And so the first thing to see which I have highlighted with these two patches in blue and red, is that the transfer for one gas seems to smoothly increase or saturate at higher wind speed. Now there are some new measurements at higher wind speed where it seems to saturate, while the transfer of CO2 increase dramatically. I mean, you have you're gaining almost 2 orders of magnitude in the intensity of the transfer. And then the second thing is that it's very scattered. You have very big differences between different data sets. One of the reasons is that it's a very difficult measurement to do. So you need to go on a ship. You need to measure your concentration of gas in the water and in the air to get the concentration difference. And then you need to measure the flux. So to do that, you need the fluctuation of the vertical velocity and the fluctuation of the gas component. So it's a complicated experiment. It's a complicated measurement, which explains the large error bars. But my point when I see this plot is that we should try to find other axes here than just the wind speed, some parameterization that depend both on the wind speed and the wave state to reduce the scatter between these data and also understand why different gases behave differently. So mainly the difference in the different gases comes from the difference in solubility. So my point is gonna be to find the right variables or the right way to make these plots to have better parameterization. And all the dashed line or solid lines that you see around here are different fits that have been done in the literature and that are used in large-scale models. Does that answer your question? Okay. So there are large uncertainties in the role of the bubbles. The way it's typically modeled, if you want to take it into account in the model, is you add a second term to your total flux, which I call here FB. And this FB is going to be an integral over all bubbles. So N here is the bubble size distribution that depends on the size of the bubble and the depth. So you integrate over the size and depth. And then this function J here is a transfer velocity for a single bubble. So it's going to depend on its size, because the more surface area, the more exchange. It's going to depend on its velocity. And then it's going to depend on its chemistry, so diffusivity and solubility. And so people have been proposing these kind of formulation, and it makes sense. But if you want to compute this term correctly, no matter what you do, you need an accurate information on the bubble size distribution. And that's not something that we had, that we knew that well. And so that's why when you look at the literature in the last 15 or 20 years, you get very, very different results about how much bubbles actually matter. And if you want to take like the upper bound of what people have been saying, it's like it goes from being completely negligible to being almost half of the total transfer. So we need to better understand and constrain the bubble size distribution. Before I go on, I just wanted to kind of emphasize on, and it's one of the reasons why I like this problem that much, is it's really a complex multiple scale problem, because you need, if you want to really bring new parameterization and provide more information and better information based on physics, you need to understand processes at very different scales. So you need information about the wave and wave breaking statistics, because you need to be able to know for typical wind speed what is going to be the statistics, what's going to be the typical wave height, what's going to be the typical scale of the wave. So you need some information on the wave and wave breaking statistics. And that's going to be at scales from like the meter for the short wave to 100 meters or the kilometer if you consider groups. Then you need information for what's happening during a breaking event. So this is a breaking wave in the lab. This is my initial picture, and that typically the breaking event, it's going to be of the order of it's going to happen at scales around between 1 and 10 meters. And then you need to understand what's happening for a bubble cloud, where scales get to the millimeter and below. So obviously you can't do everything at once, and you need to split your problem in different steps. Okay, so this is the outline of the talk. I'm going to quantify air entrainment and bubble statistics and the turbulent to phase flow associated with braking. And I'm going to do that first for a single braking wave, and then I'm going to upscale to the field using the wave and wave braking statistics. So I'm going to start by presenting kind of the methods, how I'm studying, or how people are studying single braking events. I'm going to talk about how we quantify wave braking, wave braking dissipation due to wave braking, and then I'm going to discuss how I go from information on dissipation to information on air entrainment and bubble statistics, and then I will present the upscaling. You have questions? Good. So this is a typical lab experiment. This was done at Scripps. This was part of some teaching we did at Scripps. It's an experiment that's been done for now more than 40 years. You send a focusing packet, so you have a wave tank. This wave tank is 30 meter long, or was 30 meter long. Water depth here is around 50 centimeter. You send a focusing packet, you send high frequency wave first. They travel slower than the long waves. And so all the wave meets in the middle. It's like constructive interference, and you create this braking event in the middle. It's very reproducible. Braking occurs almost at the same spot at the same time, so you can gather large data sets and look at and do ensemble average. And so what you see is this plunging breaker that entrains a large pocket of air, and then you have the evolution of the bubble cloud here. And so if you measure the wave field before and the wave field after, you can estimate how much energy is dissipated. And then if you look with cameras where it breaks, you can quantify the bubble phase. This is a similar movie. It's exactly the same experiment. The only difference is that this is taken with a high-speed camera, so it's going at 400 frames per second. So you're going to see the braking front arriving. So here you see the front, and you get like this vertical shape. Then the jet forms. The jet is going to fall back in a ballistic way. It's going to impact the surface. It entrains a large bubble cloud. You get some splashing and some ejection of drops. And then maybe if you have good eyes, you can see that you have some bubble getting up and generating drops. So this is what an experiment looks like. And then what I have been developing in the last years is some direct numerical simulation of braking wave. So what we do is we solve the Navier-Stokes equation in a two-phase flow. So here you have water and here you have air. It's incompressible in both fluids, so we solve the incompressible variable density Navier-Stokes equation with surface tension. I'm using a solver that's called Jeris. It's an open source solver, so you can go there and download it. It's one of its features that it has an adaptive grid, so you can put more resolution in the area that are of interest. So here, what is of interest in a braking wave simulation is the surface. So that's why you have lots of points at the surface, and then the mesh is decreased when you go deeper in the bug. Yeah. So surface and vorticity are the two stuff we focus on, because where you have intense vorticity is where you're going to dissipate energy. It's thanks to this adaptive methods, it's highly efficient, so you can do lots of runs and you can explore the parameter space. So this was in 2D, and then we moved to 3-dimensional simulation. So it's we do something that's kind of classic in the wave community, is we consider initially a Stokes wave, so a truncated Stokes wave, to start the simulation. And then the wave propagates, and if you put the high enough amplitude or high enough slope, the wave is naturally unstable and is going to break. And so that's what you're going to see is for a strong braking wave. We work at, I'm going to show the movie one more time. We work at fairly high Reynolds number. So the Reynolds number here is defined on the wave phase velocity and wavelengths. So it's not like a turbulent Reynolds number. The Reynolds number we work with is around 40,000. If you consider a real wave in the lab, it's going to be more around the million. So we are off by almost 2 orders of magnitude in the Reynolds number. And what I'm going to try to convince you afterwards is that even if the Reynolds number is slightly slower than what it should be, we are still getting the right dissipation rate. And then we can vary the bond number, which is the ratio between gravity and surface tension, which effectively is equivalent to varying the wavelengths. The main stuff I'm going to be varying is the slope of the wave, so it's the amplitude going from incipient breaker to strong plunging breaker. And we solve accurately the dissipative time and length scale, as well as what we need to look to air entrainment. Yes.
Excuse me.
Yeah.
Could you tell me what a Stokes wave is?
Okay, so a Stokes wave is it's a periodic solution. It's a fully nonlinear periodic solution for the wave equation. If you look at the potential, so if you derive like the equation of wave motion and you get the dispersion relation, you do that all of that in for potential flow, so without vorticity. And one of the solution for any amplitude for the fully nonlinear equations is what's called the Stokes wave. But if you do that, you normally need like an infinite number of Fourier modes. And so what we do in this simulation is we only keep the first 3 modes. So we have it's basically the linear solution plus 2 nonlinear terms. So you have a wave that is like slightly asymmetric instead of being completely symmetric if it was a linear wave. Yeah. And it's kind of, I mean, we could do exactly the same by starting with a sinusoidal wave, so a linear wave, just that since we work with high amplitude, it doesn't really make sense to use a linear solution. You could say that it also doesn't make sense to use a weakly nonlinear solution for these highly nonlinear wave, but it's a simple way to generate a breaking wave in a computer in a compact way.
Yeah, could you say a few words about how you treat the interface between water and air? Do you have some kind of surface tracking
So
module,
yeah,
or?
so the way it's reconstructed, it's an algorithm that's called volume of fluid, and we can spend time discussing about it. I mean, it's basically you are reconstructing that interface at each time step by doing like linear approximation at the grid size. And you conserve or you try to conserve mass. So in this simulation, you conserve mass up to 10 to the in percentage is better than 0.001%. Yeah, we can discuss that in detail. It's kind of, I mean, the volume of fluid approach has been used in the fluid mechanics community for interfacial problem quite a lot. It's and then it's a little bit depending on how good the code is, you get realistic or not realistic surface. Other questions? Okay. So I want, since it's going to be my main parameter, the main variable I move in the talk, I just want to insist on what it means to change the wave slope. So the slope is the ratio, is amplitude times wave number. So if you have a very strong slope here, 0.5, you get a plunging breaker. So you have a large amplitude, you create a jet, you entrain a big air cavity. This is a picture in the simulation. This is a picture in the lab. And then if you go at the smaller slope, you are going to have what's called a spilling breaker, where you don't really form the jet, but you have the surface that roll over in the front, and you can see that here in the numerics and here in the lab. And so when you increase the wave slope, what's kind of intuitive is that you're going to have a bigger impact, so you're going to generate more turbulence, you're going to have more dissipation, and you're going to entrain more air. And the idea is to quantify what is this. You're going to have more turbulence, dissipation, and air entrainment. Okay, so let's go for to describe the dissipation. So if you want to describe the wave field in the ocean or elsewhere, one of the approach is to consider the evolution of a kinetic equation. So it describes the wave field evolution in the Fourier space. So here nk is the spectrum of the wave action, which is related to the spectrum of the wave energy. So you have the time evolution of the wave action, or the wave energy if you prefer. So that's a quantity that probably Alan Newell has been talking about when he was talking about evolution. I mean, I don't know what he has been talking about, but probably about wave action and wave spectrum. And so the time evolution of this spectrum is going to depend on what's called source terms. And so you have three source terms for ocean waves, which is your input of energy, the nonlinear interactions that are transferring energy through the scales. So for ocean gravity wave, it's a 4-wave interaction process, so that you can have both direct and inverse cascade. And then you have, so input is going to be by the wind in the ocean. And then you have dissipation. And dissipation is going to be due mainly to braking, and that's what I will be focusing on here. And so the way it's been described in a comprehensive way is due to Phillips in 85, which wrote the dissipation as the integral of the dissipation rate per unit length of braking crest. So it's kind of a 2D dissipation rate, because it's the dissipation in a plane. You assume that if you look from above, so you have the wave crest that has some length, and you assume that it's going to be all the same towards this transverse direction, right? So you define a dissipation rate per unit length of braking crest, and then you integrate over this quantity lambda CDC, which represents the statistics or the distribution of length of braking crest. So if you look at the ocean from above, this is an image from an airplane. This is a big braking wave that just occurred, and so what we define as lambda is this length here, right? So that's the length of the crest, the length of the braking crest, and this crest moves at a certain speed c. And so if you have movies of this, if you fly over the ocean and you take movies of the ocean surface, you will get a statistics of these lambda as a function of the velocity. So basically this quantity is going to come from field measurement. And then this quantity, so the dissipation for a single braking event, you can investigate it in the lab or numerically. And what Duncan proposed in 81 is to say that through dimensional argument, he said that this dissipation depends on the phase velocity of the breaker to the 5th power, and then you have gravity and density. And he showed this 5th power, that this 5th power was accurate through experiments. And in his paper, he initially assumed that B, which he called the braking parameter, is going to be a constant. And so something that has occupied people for a while was the question if B is really a constant. And so this is kind of 30 years of lab experiments that have shown pretty clearly that B is not a constant. So here you have the wave slope that goes from 0.1 when you start having braking wave in certain condition in the lab, up to 0.6 almost, which is kind of the highest slope you can get in the lab. And you see that it increased from 10 to the minus 4 to almost 10 to the minus 1. Okay. Yes, sorry.
About the parameter lambda,
Yeah.
capital lambda is, so you said it's observed, and then is there some theory for the distribution, or
yes
it
and
looks
no.
something?
So I will show some field measurement at the end, so I can discuss a little bit. There is, in this paper, he has a scaling argument to say that it should have a slope c to the minus 6, and that's about it. That I can and then you have people that are people are measuring it more and more, and so you start having some data, and so people are trying to make scalings out of it. So somebody in Ken's group has proposed a scaling a few years back. The data are pretty noisy, so I have played with the data, and you can propose many scalings. So and in terms of so the c to the minus 6 is observed within the noise of the data. The amplitude is open. I mean, how it depends on the wave parameter and wind parameter that's an open question. Theoretically, experimentally, I mean, in the field we have data, kind of, but to really explain it, it's open. Other question or?
On your next slide.
Yeah.
So S is it a characterization of the initial condition
Yes,
for the wave?
it's the in all these experiments, it's the maximum linearly predicted slope. So if you do a focusing packet, you send typically you send like n components. So and so if you sum the slope, the initial slope of each component, you get the maximum linear slope, and it's actually the slope that is observed at breaking within like. I mean, it's directly related to the slope at breaking. So this is, you can say, I mean, in the scaling argument that's going to come in the next slide, we are going to explain this curve by saying that S is the slope at breaking, but in all these experiments, you can actually know it up before breaking occurs, and then you can verify by measuring it that it's actually the slope at breaking. Yes.
So on the previous slide, you wrote an equation for nk. So are you looking at dissipation at a given wave number? This dt of nk?
No, the way, well, so no. Because the dissipation here, the way it's written here, the dissipation is integrated.
So it's the total wave action.
So it's a total wave action, yeah.
Okay.
Yeah.
Thanks.
Okay, so I'm going to go through a scaling argument that was proposed by Drazen et al. In 2008 to explain the evolution of the breaking parameter as a function of the slope. The initial idea comes from a classic result in turbulence, which is to say that the turbulent dissipation rate epsilon is going to scale like the velocity to the cube divided by the length scale of the flow. And what we say, or what Drazen et al. Said, is that this velocity is going to be the velocity of the falling jet, and the length scale is the height of the breaking wave. So you have the velocity that's going to set your turbulent flow, and you have the height of you have the scale of your turbulent flow. And then they assumed and then verified experimentally that this velocity, this vertical velocity, is a ballistic velocity, so it's square root of gh, h being still this height, because that's the height from which the jet is falling. And so you get that epsilon should be g3 over 2, h 1/2. And then to recall, to kind of be consistent with the framework of the dissipation from Phillips, they connected this turbulent dissipation rate that is created with the dissipation rate per unit length of breaking crest epsilon sub L by the geometry. And they assumed that the relation is to say that the local turbulent dissipation rate is related to the total one per unit length of breaking crest, saying that the turbulent cloud is roughly extended over h square. So if you do that, you end up with epsilon sub L that goes with the height of the wave 5 over 2. And then you use the dispersion relationship for deep water gravity wave, which say that the phase velocity goes like square root of g over k, and you define the wave slope as hk, and you end up with this formula for epsilon sub L, and this formula is completely consistent with the one defined previously if you say that your breaking parameter is s to the power 5 over 2. I think there is a question there, or you have a question?
I have also a question. Yes. What is the dimension of epsilon? It's
epsilon here. Well, it's just u cube over L. So it's it's the classic dissipation rate.
Is it a power per unit of mass?
It's so it's L over. So epsilon is so it's L3 t minus 3 divided by L. So it's L2 t minus 3. So that's the turbulent. That's the dissipation rate in turbulence
So it's
without the density
so
in front
the
of it. basically.
dissipation rate is assumed to last for a finite amount of
Yes.
time.
Yeah.
And
Yeah.
so then you will have to multiply this by
Yeah.
the duration of the event. or
So
something
the
like that?
way, yeah, basically the way it's gonna be. So that's a very good question, and it's a very practical question. Is that so breaking events are transient, and so everything we are kind of gonna consider quantities that are per unit breaking time. And so this is gonna be your dissipation rate for the amount of time that the breaking event occurs. Does that answer your question? Or? Yes. I will never do it in 1 hour, but go ahead.
Okay, just a basic question that
Yeah.
should not take anywhere near an hour. So I look at this picture and I see a bunch of different slopes. I see a slope like this, and then there's a slope here and a
Okay,
slope
so
there. So
it's the
what's the slope?
The slope is h, so the height of the wave over the wavelength. So the wavelength would be something like it's basically the okay. Maybe I should have defined the wavelengths for wait. So if you have a linear wave, right? That's your wavelength, and so the wave number is 2 pi over lambda. Okay, and so if you have a breaking wave, you can't really define the slope anymore because you don't really have this geometry. But what we do is, so you have something that looks like this, is that you're gonna define your wavelengths by being what you can do to define an equivalent to this, right? And the k that I'm going to be considering in all of this is going to be the central wave number of the packet. Okay. So the typical wave number, if you want. Okay. It's kind of, I mean, it's a very good question in the sense that people are really debating about can we define things in the way that we are defining it and things like that. So, okay, thanks. So anyway, you end up with this scaling, and it works quite well. So if you get back to my experimental data, you have the 5/2 scaling that works pretty well for the high slope. For the high slope data, and then it doesn't really work for the weaker breaker. And to explain and to put everything on a single curve, what Romero et al. Did is that they introduced a breaking threshold. And so introducing a threshold is kind of arbitrary, but it makes sense in the physics of a breaking wave because it's a problem with a threshold. Below a certain amplitude, the wave doesn't break. Above a certain amplitude, the wave breaks. And this is completely empirical. It's fitted to the data, and we have no clue how to predict it. So you end up with a single formula where you have one parameter that you have a physical interpretation for it, even if you can't predict it, and then this is a fitted constant. Okay. And it works for pretty much all the data that you can find in the literature. So this is a good test for the numerics. So in the simulation, you can measure all the energy components, and so you can measure your dissipation rate. So I'm going to go fast on this. And if I superpose my numerical points, which are in blue and red, to the experimental data, you get a very good agreement. For the strong slope, you get discrepancies here around 0.3 between experiments and numerics. And that's because in my Stokes wave, so in my simulation, my initial conditions are very different from what is done in the lab, and so I don't get the right threshold. So I get another threshold, which is completely related to my numerical constraint. So if I do a numerical simulation that's exactly mimicking the lab, then I get exactly the same threshold. And then these points are kind of interesting because they correspond to waves that are not exactly breaking, but they are what's called parasitic categories. So it's when it's short wave, when you have a lot of surface tension. So instead of breaking, you have a small capillary wave that propagates at the front of the wave. And what's intriguing is that it seems to follow the same dissipation as the weak breaking wave reported in the literature. Something that's also very interesting and that I will not talk about, but you can ask me about after, is that we get the same dissipation rate in 2D and 3D. And so at this point, what I hope I have convinced you is that we have some understanding of what's happening when a wave breaks and how much energy is dissipated, and we have simulation that reproduce these dissipation rates. So now that we are confident that we are solving correctly the small scale related to dissipation, we can look at air entrainment. And we are going to follow the same strategy or the same framework as was done for dissipation. So dissipation, we wrote that it was epsilon sub L integrated over the breaking statistics. So we are going to keep this structure, and we are going to find an equivalent for air entrainment. So we're going to say that the total volume of air entrained by breaking wave is the integral of a sum function VL, which is going to be the volume entrained by a single breaking wave at a given scale, and then integrate it over all the breaking events. So we don't have to worry about this part, because we know that this part we are going to take the field data. Or at least for now, we don't have to worry about it. And then the final goal is to get the gas flux. And getting the gas flux would mean computing how much gas is transferred for a given volume, and then it's also going to depend on the chemistry. So I have not done that yet, but it's work in progress. And so now we are going to try to get this function VL, and to get the volume, you need to get the bubble size distribution. Okay? So the state of the art on the bubble size distribution is pretty much all in the paper from Dean and Stokes in 2002. You have several studies that are confirmed what I'm going to say about this plot. But that's basically what we knew or know on the bubble statistics. So here it's the number of bubble as a function of size. And it goes from 10 to the like a little below 10 to the minus 1 millimeter to 10 millimeter. So the biggest bubble that are observed under a breaking wave in the lab. Yeah, and these experiments have been done basically in the same configuration as what I showed in the introduction. So the movies that I showed, you can imagine that they gave you these data, even if it was 2 different experiments, but it's the same protocol. Okay, and so what you have to see on this plot is that you have a sharp change in your bubble size distribution for a scale that's around the millimeter. For bubbles smaller than 1 millimeter, you have kind of a weak dependency in radius. And then if you go above 1 millimeter, you have a very steep slope that's close to -3. And the scale that separates these two regimes is called the Inze scale, and physically it's the scale at which surface tension prevents breakup by turbulence. So you're just building, in a sense, you're just building a length scale that compares the intensity of the turbulence with the strength, with the surface tension. Okay, it's strictly equivalent to define a critical Weber number if you wish. And so you have this steep slope for the big bubbles. And the big bubbles are important in understanding the total entrainment of air, because that's where the volume is, right? More than 95% of the volume is contained in this part. However, understanding this part is key for gas transfer, because the small bubbles are going to stay longer in the water, and they may dissolve completely. Okay. And this -10^3 slope was explained by a scaling argument by Garrett by assuming a steady model for the breakup of the bubbles. And what he said is that if you consider that surface tension doesn't matter, which basically means you consider a bubble larger than the Inde scale, the bubble size distribution should depend linearly on the inflow of air, and he called that Q, and then bubble radius and turbulent dissipation rate. And once you have assumed this linear dependency in Q, you have only one-dimensional solution, which gives you this R to the -10^3. So what is remaining as question is, okay, we have observed this stuff. I don't know if I have convinced you with the scaling argument, but this is observed. But we have no idea what's the mean airflow rate. And this should be an epsilon. If you think about the airflow rate, okay, the airflow rate is likely to be related with the height of the breaking wave, because the higher the wave, the more air you're going to put into the water. So this this airflow rate should be related to the water height, and we have seen that the turbulence is related to the water height. So these two stuff are likely to be related. So we would like to find a final scaling in epsilon, especially since now we can say that we know what's epsilon as a function of the initial wave variable. Okay, and then it would also be nice to have some information about the time evolution to constrain the total time scale. All right, so to do that, I'm going to use my numerical simulation and analyze the bubble statistics and the total air untrained under breaking waves. Okay, so this is a plot of the bubble size distribution as a function of time. Here you have the bubble radius, here you have time. Entrainment, breaking occurs year around time equal to 1. The time is normalized by the period of the wave. So when the impact occurs, the interface looks like this. So you just got the impact, you have entrained the large pocket of air, and then you have satellite bubbles. And so the satellite bubbles are the small ones present here. And then you have some short time over which the cavity collapses and you create this large bubble plume with very different sizes. So you get this very broad spectrum of bubble, very broad distribution of bubble. And then the distribution decays with big bubble rising back to the surface and bursting and breaking into smaller pieces. And then basically once you are here, it's over, not much is happening anymore. You just have the small bubbles that stay in the water because they are neutrally buoyant. But the turbulent event in itself is kind of over. So what we did is we looked for a connection with the time evolution of the dissipation rate. So this is the time evolution of the dissipation rate integrated over the whole volume, and here is the same plot as before. And what I saw is that there is a time lag between the moment you start entraining air here and the moment where you reach the maximum dissipation. And so this time is typically the cavity collapse time. And then you can do an imperfect, but that's the best rescaling we could do by normalizing the time evolution of the bubble size distribution by the dissipation rate and taking into account this delay in the bubble formation process. And so these are the bubble size distribution at different times from the formation of the bubble size distribution to kind of like the end of its life. And what's remarkable is that you get a bubble size distribution that scales with the dissipation epsilon and then always has this minus 10 or 10^3 power law, always being during the time of the breaking event. Okay, so it lasts for about one wave period. You have this statistics that stays, that evolves in time according to the level of dissipation in the system. Okay, and we are going to use this idea that there is a relation between the total volume of air being entrained and the level of dissipation. And that's actually something you can also observe if you change the slope of the wave. You see that the more dissipation you have, the more bubble you have. And so the idea behind that is that there is some sort of equilibrium or scaling between the work done against buoyancy forces to put air in the water and the mechanical dissipated energy. Okay, so we are going to work from this hypothesis, and then you can formalize this idea by just writing what is the work done against buoyancy forces. So it's this big integral, which is an integral over the bubble size distribution. So times air cubed, so that's the bubble volume, times the vertical velocity. So that basically gives you the buoyancy forces with density and gravity here. And you integrate in space and time. And you say that this should be balanced by the dissipation integrated over the volume. And B is a constant that we are going to determine experimentally or empirically. You can do a little bit of massaging of this equation. You separate variable and you introduce a mean vertical velocity, and you end up by writing this stuff as this scaling relationship, which is to say that the dissipation is the turbulent dissipation rate times the volume of water, and that scales with the volume of air times GW, which is the buoyancy forces. And I mean, saying that is exactly the same as saying that. It's really just different ways of explaining of proposing the same idea. And what it means is that your ratio of volume, so your volume of air per unit volume of water, VA over VW, should scale like epsilon divided by GW, which can be seen as a non-dimensional number that compares dissipation and buoyancy forces. Okay? And so then what we did is we tried to reconcile this idea with the Garrett et al. Model. And one of the reasons is that since this stuff gives us the right statistics, it was kind of hard to get away from it. Or another way to say it is that we did not find another way to explain the slope of the bubble size distribution. So we are going to define the airflow rate Q as the volume of air untrained per unit volume of water per unit time. And we are going to say that this time is the breakup time. And we are going to estimate the breakup time by getting back to this classic idea on the time scale and turbulent flow by saying that the turbulent breakup of a bubble, tau, so the breakup of a bubble of size Ri, so that's going to be tau I, is going to scale like the size of the bubble divided by the intensity of the velocity fluctuation at this scale. And the velocity fluctuation at this scale, U, is going to be epsilon Ri power 1/3, according to this equation. So I'm still just using this stuff. And that's the time for one bubble to break into 2 or 3 smaller bubbles. And the scaling for the time was actually observed in some laboratory experiment by Martinez-Bazin in 1999. Okay, and then we do the assumption, which is a big one, to say that, okay, it's a sequential process. So you start with big bubbles in the system and they break up into smaller one sequentially. So you can define your time at each breakup, and so you can write that the total time is just the sum over each time. And it gives you a geometric series, and so you have epsilon minus 1/3 that kicks out, and you end up with a new variable or a variable that you have to consider, which is the maximum bubble in the system. Okay, and so that means that if you now use this tau in this equation, that your bubble size distribution is your ratio of volumes time the maximum bubble size power 2/3 times r minus 10/3. And now you should have seen me coming. This stuff was, we proposed this scaling for the ratio of volume, and we got this by adapting the model from Garrett, and so we end up with this relation. And if you keep my big equation, if you go through the algebra, you can track the constant, and you end up by having my constant b divided by 2 pi here. And so you have two pieces in this like model, scaling model. One comes from the idea of turbulent fragmentation, and one comes from the balance between buoyancy and dissipation. Do you have a question on this? Okay. And so now we can try to use that to compare lab data and numerical data. And so this stuff here is basically the bubble size distribution rescaled by my model. And then in colors, I have different numerical data for increasing slopes. And then in black, I have the laboratory data from Dean and Stokes. And you see a reasonable rescaling in the range of basically 1 millimeter to 10 millimeter. So here it's rescaled by the maximum bubble, but if you stay in real units, it's basically in the range of the bubble that are being broken in pieces. So we have a way, I mean, we are putting all the data together in this part, and then this part is completely unknown. And if you look at other lab experiment, this part actually everybody gets a different solution. And I am not having any, I can't say anything about these bubble scales from my numerics because these bubble sizes are not resolved in my numerics. And then we can look at what's the prefactor, so what's B, and you have estimation in the literature of this ratio between the energy in the bubble and the total dissipation rate, which corresponds to B, which says that it's between 5 to 15%. And if you plot the 5 and the 15%, you get right on top of our data, within the scatter of, within our precision. So we have a model for the bubble size distribution, and now we can apply it to the field. And so we are going to apply it to the field by basically the function that I showed you for the bubble size distribution is what I'm going to use to compute this VL, and then I'm going to take that from the field. So the way I use my model from the numerics and the experiments is by saying, so the total volume of air for a single breaker is simply the integration over the bubble size distribution over all bubbles. And then the volume of VL for dimensional reasons is defined as the volume of air per unit time, so per unit event of breaking, per unit length of breaking crest. So that's my total volume divided by the time of the breaking event and divided by the length of breaking crest. You can see from lab and numerical data that this time goes actually like the height of the breaking wave divided by my mean rise velocity, and that's what we're going to use. And so you end up by when estimating this formula by finding that the volume should be B divided by G, and then you have the ratio of your breaking parameter that comes from the dissipation that is in this formula divided by HK, and then this is the third moment of lambda. So I can show you the detail on how to go from this to this, but that's what we get. And so basically this third moment of lambda, the C3 lambda C, we're gonna estimate it in the field. B, we're gonna estimate it by visible imagery, and then B over HK is related to the wave field and the wave dissipation. So this is a movie of what I showed previously. So this is taken from an aircraft. It's flying over the ocean, and the aircraft is flying faster than the wave is breaking. And so from that you can measure the fronts of the breaking wave and their speed, and you can build lambda C, and that's what lambda C is looking. That's what it looks like, and you have basically this very steep dependency in the speed, which is roughly c to the -6, and you have a maxima that's around between 1 and 2 meters per second, depending on the conditions. But you can get that for different experiments. And then we can evaluate what I have called this volume flux of air. And you have two components to evaluate this. One is to evaluate this B over HK. And this is the way we choose to evaluate this is to say, okay, we have initially showed that the breaking strength or the dissipation depends on the wave slope to the power 5/2. So what we're going to do is we're going to take the slope spectrum, and we're going to say that the slope spectrum can be used as the wave slope of breaking wave. So you're going to have basically something that's scale dependent, because your slope spectrum is going to depend on your scale. But your slope spectrum is estimated from wave spectrum measurement. So Ken's group has been doing wave spectrum measurement using LiDAR, and they get a pretty incredible resolution. So this is a recent plot from them where they measure the wave height with these LiDAR, and so they get basically the spectrum from scales around 100 meters here up to here. You are at wavelengths that are around 50 centimeters. And they see, this is kind of a digression from the subject, but you see two slopes in the spectrum. One is a -5/2, which can be explained by nonlinear, which means that it's a nonlinear interaction that are building this part of the spectrum, and then you get a steeper spectrum because of dissipation. The point is, from this you can get this part of my integral by doing some assumption. And then this is what I have already shown. This is lambda, and so you get lambda and you have C. And then you go from the K space to the C space using the dispersion relation, which is again an assumption because once the wave break, the speed of a breaking front has no reason to follow the dispersion relation. But that's the assumption that we make to go from the space in wave number to the space in speed. Yeah. Sorry.
Just quick, can you say again what lambda means?
So lambda is
Because of the units, I'm confused.
okay, yeah. So lambda CDC is the length of breaking crest traveling at a speed c. So then lambda as the scale of a length scale divided by velocity. So it has yeah. Okay, and then this is the output of this big integral which combine my idealized model and the field data. We don't have much time, so we're going to skip. Don't look at the top, just look at the bottom. This is this volume flux of air as a function of the white cap coverage. The white cap coverage is the average area of white cap, so the average area of white patches in the ocean. And people have been using that because it's easier to measure than getting something that's dynamical. You can just measure white stuff. So people have been using that as a proxy to estimate the intensity of breaking wave. And then you have a parametrization in the literature that relates the white cap coverage to the wind speed. And so here you have this volume flux as a function of white cap coverage. And we see, and the different symbols are different data sets in the sense different field experiments. So this one was in the Gulf of Mexico, and this one was in the Pacific Ocean, for example, in different years. And one thing that's interesting is that we see almost clean linear relationship, but different ones for each field experiment. And one of the reasons we think that's the case, it's because each measurement of the white cap coverage is going to depend strongly on how much light you have, what threshold you consider when you do your image processing and things like that. So it's actually tricky to compare different data sets from white cap coverage. So that's one stuff. The second stuff we see on this plot is that we have no clean relationship between the volume flux of air and the wind speed. You basically have kind of a big mess and variation of what I think what we have computed as the total volume of air. For same value of the wind speed, we have variation of an order of magnitude in how much air has been entrained, which is coherent with the first plot I showed in the introduction that shows that you have very large differences in the gas flux. Okay. If you were to assume that all my bubbles are completely dissolving and that this stuff is exactly the gas flux, which is wrong, then you would get again this picture that the gas flux does not depend monotonically or in a simple way of the wind speed. Okay, and then we played with the data and we tried to find something better, still fairly imperfect, but a little bit better. And so here you have this volume flux normalized by the velocity of the peak of the spectrum as a function here of the wave age, or here as a function of u star divided by the ballistic velocity square root over gh. And we get at least monotonic relationship. So you still have big scatter, but you have something that is slightly more organized. And so you can fit this relationship and hope that they are going to be relevant for gas transfer parametrization. And so with that, I'm going to conclude. So we have brought a general understanding of the turbulence associated with braking. We have modeled the bubble statistics and the total volume of air. And we are proposing a strategy to upscale to the ocean. And one thing that I should mention also that relates to your question about lambda is that the scatter that we have here comes from the scatter in the measurement of lambda. So I mean the scatter you have in lambda is almost exactly the one you have here. Yeah, thank you very much. Oh yeah, okay. And this approach I believe can be applied to so combining lab experiment, numerics, and simplified model can be applied to other problems related to ocean-atmosphere interaction. Thinking about spray, drift, and Lagrangian. I mean Lagrangian drift and horizontal mass transfer, gas transfer, etc. Thank you very much.
Question.
Wait, so Can I ask my question again now? For example, imagine you have a tropical cyclone and U is way too big and you can't even define the surface. Or like, are you interested in those high velocity problems?
Yeah, so my answer to this is that all of this is not gonna be relevant anymore because you don't have a dynamic that you can define of wave and breaking wave, and you probably have an interface that's completely destroyed, and you have a mixture of air and bubble and at very high wind speed, and you have so the way I would like to attack this problem is by doing simulations of a flow which you have a bunch of drops and bubbles that are mixed, and emulsion of drops and bubbles that are mixed with a very strong wind.
So, for instance, there is the empirical Beaufort scale for the wave as a function, the state of the ocean
as a function
as
of
a function of the velocity. And so, it describes fairly different state of the ocean.
Yeah.
So probably what you do is related to one of this regime. Or
So what I do is related, I would say, when you have wind speed below 25 or 30 meter per second, which after that you get into the regime where it's more hurricane and you probably have a change of regime in all of this. I guess that's my, but we don't really have, there is not that much data, and so it's
I just take one question.
Yeah.
I have a question about the white cap coverage.
Yeah.
So is it completely scattered over the ocean, or they seem to be order of magnitude? Is there an average value for this, or what?
At some point I had a backup slide on that. I don't know if I still have it. Yeah, this one. So that's from a review from Deloitte in 2011. And I don't know if he got all the white cap coverage data he could find, but there is a bunch. And so you have wind speed, it goes from 0 to 25 meter per second. And then you have everything on top. And so the black line is the first one, so that's the historical parametrization from Monahan in the 80. And so that's what's typically used to relate white cap coverage to wind speed. So again, you have large scatter in the data, and you can sync, and some of the scatter is due to the fact that everybody is measuring the white cap coverage in a different way. So yeah.
So just a quick follow-up comment about Tom's question.
Yeah.
So in the tropical cyclone research community, we really care about the LC exchange because it is important for the development of tropical cyclones.
Yeah.
So a while ago, Professor Michael Bell and Carrie Emanuel had some estimates of the exchange. In a situation of high wind speed.
Yeah.
But that is from the budget of the momentum and the and also some energy analysis. I think it will be interesting to test your model against these estimates. Yeah.
Okay. Thanks.
Other questions?
It's about the conclusion. So you were talking about mainly gas transfer, but can you say something about, for instance, momentum transfer? Do these bubbles affect the momentum? I don't really know what's, because you somehow... Or heat transfer?
So I think to say something relevant about momentum transfer, you need to do something with the wind. And everything that I have done about wave and breaking wave was with no wind. So I would not try to use the simulation that I have now to say something about momentum transfer. We could look at heat. Heat and gas is kind of the same. They are related. So basically, I will do the heat when I do the gas. And so to do that, you need to change the methods to something that's compressible for the air, and to have some gas model inside and some chemical exchange model inside, so that you can redo this study with the chemical exchange. And then if you do that, then you can look at the heat at the same time. We could look at the heat already in the present configuration, just has a tracer, and but I have not done it.
Because I mean, my question was mainly, do you know if these bubbles somehow have an impact on the
No, I don't
No.
know.
the momentum?
know.
Okay.
Yeah.
Okay. Thank you.
Is there another question? So we can thank Luc again.
Thanks. And before we go for dinner, I have two quick announcements. One is that I am organizing a workshop on numerical methods in multiphase flow at Princeton in November. So if you are interested in this picture, you can come. And the second one is that I am looking for a postdoc at Princeton. So if somebody is interested, please contact me. Thanks.